Okay, so taking a look at a carboxylic acid reacting with an amine. So the first thing that's going to happen is the carboxylic acid is going to be, of course, an acid. And the amines are actually really good bases, so they're electron rich. So the amine is going to deprotonate the carboxylic acid. That's always going to be the first step. This makes the carboxylate, the negatively charged, resonance stabilized, deprotonated carboxylic acid, and it makes the amine. Right, so essentially it makes the salt, right? A plus charged nitrogen. Now, under normal conditions, this would be it. Nothing else is going to happen. But you can force this to react and to form this, the actual amide. And you also generate water. Now, I didn't ask you guys to know the mechanism for this, but you can imagine what it would be. You'd need another amine. So you're going to need an excess of amine, at least two equivalences, at least two of them. And essentially, right, when there's a lot of heat, and I'm talking like 300 degrees and maybe some pressure, you can get this reaction to go. Because the problem is, why this doesn't go, this is an okay nucleophile, right? But that carbon now is not very reactive. And why is that carbon not very reactive now? What? Well, the resonance, right? This whole area right here is electron rich now, right? There's a negative charge. We're asking this to be an electrophile when it has a negative charge. That's kind of weird, right? And because of the resonance, this carbon, right, is not as delta plus as you'd expect. But if you really, really force it, put a lot of energy into the system, you can get this to go. And again, I didn't ask you guys to know this mechanism, but here it is, just so you can at least see it. It actually looks similar to one you've done with the lithium, alkyl lithium. We did this, right? Where you got something like this maybe, but it wasn't. There's no plus charge, but you could do a bunch of proton transfers and eliminations, and eventually get to here after following a couple steps. Like I said, I'm not asking you to know the mechanism, but this is what the idea behind this is. So essentially, to make this work, you need a lot of heat and a lot of energy. You should for sure know this first step, this acid-base reaction. That you should understand. How we got all the way to here, I'm not asking you to know just now. But you should know if these two things are around and there's a lot of energy and heat, you're going to make that amide. So let's take a look at a Asterafication, but an intramolecular esterification. So we were in acidic condition, so H+, is catalyst. It's got a carboxylic acid and an alcohol that's inside one molecule. So we've done where there's a alcohol as a solvent. We could put a solvent here. It doesn't really matter. You could say, oh, ethanol is a solvent. But at the end of the day, an intramolecular reaction is necessarily faster than an intermolecular reaction. So molecule will react with something inside itself first than it would with, right? It's harder to have two things run into each other than to have one molecule find a way to react with itself. So what's the first step going to be? We're in acidic conditions. So the first step is going to be protonation. And we protonate the oxygen of the carbonyl group, right? Will you protonate this alcohol? Sure, you probably could, but it's just not going to lead to products. And this is probably the most electron-rich oxygen anyways, because you can think about resonance structures to make that more electron-rich. Okay, so what that does, why do we do that protonation step? That makes this carbon of the carbonyl group that much more reactive, right? It increases its reactivity. That's why we do this. So we protonate. Now we have the alcohol that is actually within the molecule. So it reacts with the carbon in the carbonyl group that we've just made more reactive. So that's an addition step. We're adding something in. Got to be careful here to make sure we don't number our carbons. And oxygens 1, 2, 3, 4, 5. So we're making a 5-membered ring. So 1, 2, 3, 4, and 5. Now we gotta make sure we add stuff that was all on there. So what's the oxygen still had that H on it. Carbon 1 had a OH on it. And it also has another OH on it. And I need to remember, of course, to balance my charge. So where should there be a plus charge?
5.
On 5. Very good. Great. So now we have a tetrahedral intermediate. Tetrahedral intermediate, we ask ourselves, do we have any good leaving groups? And our best leaving group is actually the thing we just added. So instead of kicking that off, we want to do a proton transfer. So we're going to lose one of these OHs as water. So we can do a proton transfer. I'll show it with the arrows. Why not? You could also just write proton transfer. That's fine. If you show the arrows, show both arrows. All this is doing, right, is making one of these a better leaving group as water. Right, these Fischer esterification reactions are all dehydrations. You lose water. So now we're here. We have the same tetrahedral intermediate as before. Now we've moved that hydrogen around. So now we need to write esterification as reactions of Fischer esterification. So that's a dead giveaway. What kind of functional group are we making at the end of the day? An ester. Right. Ideally, you'd be able to look at this and immediately draw the product. And that would help you, right, do the mechanism. You should be able to do that. Right, that way you know exactly where you need to go. So we probably all know we're going to lose, this is going to get kicked off. But then to regenerate a catalyst, we also lose that H at the same time. Right? This is similar to what we did in lab when we did a Fischer esterification. Right? But now this is a little bit different because we've actually made a cyclic ester. These are called lactones. And of course, generated water. 1, 2, 3, 4, 5. Oh yeah, sorry. This of course would be the final step is a elimination step, which also is coupled to a deprotonation step too, I guess. There's elimination and deprotonation there at the same time. So Grignard reaction feasibility. So Grignard reagent feasibility, I guess we'd say. So the thing about Grignard reagents, there's only certain types of starting materials that work well for Grignards. So Grignards, you need to have a bromide, right? So alkyl bromide, and the magnesium inserts itself into that bond. Right, it takes a carbon in both these cases. This carbon here is delta plus, it's an electrophile, and magnesium jumps in that bond. And what happens is that carbon that was an electrophile, delta plus, becomes a nucleophile, delta minus. The problem is certain functional groups are not compatible with Grignards. So think about a Grignard as like a really, really reactive negative charge, right? Carbanion, a really reactive base. So what kind of things do bases react with? Bases will react with electrophiles. So if you're going to make a Grignard, within the molecule that is your Grignard, you can't have any electrophiles. So what are some examples of electrophiles? Well, aldehydes, right? The carbon of aldehydes, ketones, carbon ketone, like all the carbons of carbonyls are usually pretty good electrophiles. But so are all the hetero atoms with hydrogens on them. So OHs, NHs, pH, SH. Those are also really slightly acidic, right? They're electrophilic. So in this case, this reaction actually won't work, because as soon as if this ever did form that Grignard there, this negative charge would react right there. So it just won't work. Now here's an ether. It's a little different, right? So that's not necessarily a really good electrophile. So this will actually work and will make the Grignard reagent you'd expect. So the thing is, when you make Grignard reagents, you just got to be careful about what other functional groups are in that same molecule. Because a lot of times you make a Grignard, you want it to be a nucleophile to react with another molecule that's an electrophile. You just got to be kind of careful what other functional groups are present. No electrophiles, no good electrophiles.
So
Which
it goes like in NH.
NH would be a problem too. NH wouldn't work. Yep. Any other electrophiles wouldn't work. So this is a sapling question. We have essentially here 5 different molecules, 5 different functional groups. So the first one, what kind of functional group is that? An al. That's a aldehyde. Aldehyde. An O8. I know what that is. That's a ester. One bromopentane is just an alkyl halide. So these are not the right products, right? I'm just drawing out basic examples. Hex means how many carbons? 6. Very good. Hexanol would just be a alcohol. And hexane nitrile, of course, would be a nitrile. Good. So first thing you need to just recognize that. You just need to know what a hexanal is, right? You know, what's an aldehyde or what's an ester, what's the nomenclature, that basic nomenclature. And then they ask you to find reagents that can convert each of these star materials into a carboxylic acid. So now it's just kind of a base way to figure out what does each thing do. So let's take a second to think about that. All right, so we need to turn all of these into a carboxylic acid, and we need to know the reagents to do so, right? So whatever we need to do to turn these carboxylic acids. So an aldehyde, I know at least 2 reagents you can use to get an aldehyde to turn into a carboxylic acid. One of them is, actually there's maybe more than that even, that we've learned about. Aldehydes, you could use chromium. You could use KMNO4. And you could even use Ag2O. So there's at least 3 ways to turn an aldehyde into a carboxylic acid. What about an ester? How do you turn an ester into a carboxylic acid? You know, 2 ways to do that too. NaOH. So there's, right, it's not, this is, don't go crazy here. There's one way is NaOH, which is a acidic or basic way. That's a basic way. So there's a basic way to do it. What's the acidic way going to be? H plus and water. And I think we went over something similar to those kind of mechanisms that turn esters, any ester, right? One way is with base, NaOH, and water probably. And the other way is H plus and water. Sometimes you need to heat these up too, but acidic and basic. So it turns an ester back into a carboxylic acid. What if you wanted to turn an alkyl halide into a carboxylic acid? What would you need to do? Make a Grignard. Right? You could do there's 2 ways to do this too, right? Which would this be? This would be the make the Grignard and then CO2. That's right. And step 2 is CO2. Good. And then usually you have to do a step 3, like H plus, to get it protonated, whatever. What's another way to turn an alkyl halide into a Grignard? The other way to add 1 carbon with nitrile, right? So that'd be the CN minus. And then you need to turn in the carboxylic acid. What do you need to do? How do you turn a nitrile into a carboxylic acid? H3O plus would do it, or H plus and water. And actually, nitriles will turn into carboxylic acids with H3O plus and water, or that's an acidic way. Guess what? I think we did this, maybe. But also, NaOH will turn nitriles into carboxylic acids too. I want you to do the acidic way. Write out the basic way, see if you can do it. Okay. So I'll show the acidic mechanism to turn a nitrile into a carboxylic acid you've seen before. I'll redraw the basic one when we get, you can imagine when we get there for this, the nitrile. There's 2 ways to turn a nitrile into a carboxylic acid. H2O plus, NaOH. And I'll show the mechanism for that. But before we get there, how do you turn an alcohol into a carboxylic acid? What are two ways to do that? Chromium and CM104. One of those two will work. Ag silver 2 oxide only works on aldehydes actually, so it's selected just for aldehydes. So chromium or CM104 will do it. If you wanted to stop at the aldehyde, you could use PCC or DMP. So be thinking of all that kind of stuff. All right. How do I turn a nitrile into a carboxylic acid under basic conditions? So the first step is going to be addition, right? Because we're in basic conditions. All right. Oh, let's see. We could do a proton transfer. There's usually some water floating around in these reactions. So we regenerate our OH minus. So it's a deprotonation. You can think of it as a proton transfer if you wanted to. Remember, the end goal is we're going to lose NH2 minus or NH3. So the same end goal as before. With acidic conditions, we're just, right, different charges. So this can react here. Right, again, remember, we have to add 2 oxygens. We're turning this into a carboxylic acid. So addition step, tetrahedral intermediate. Proton transfer. Then we'll do an elimination. And this will be a tough one, but because N8, you can imagine N2 minus is not exactly a great, NH2 minus is not a great leaving group. But if we ever do form any of this, what's going to happen right away? It's going to immediately react with the carboxylic acid. So you're going to make NH3. NH3 is a gas. We're done. So we actually don't make, right, in the basic conditions, what you make is the carboxylate itself. And NH3. Right? Because you start with a negative charge, you got to end with a negative charge, overall negative charge. So that's why usually in basic conditions you do the nucleophilic part first, and then the second step's always acidic, right? If you've seen that, remember we've seen that? That's people get confused. It's like step 1, step 2. It's like, wait, there's acid there. It's acidic conditions. It's like, no, that's the second step, right? The reason why you add acid is because now, right, that protonates this, and that makes it soluble in an organic solvent. So yes, you can do some organic chemistry with it, right? Because it's super polar. So that's the basic conditions way to turn a nitrile into a carboxylic acid.